Hi, everyone. Welcome to the SETI seminar. Today is Tuesday, September 27th, and our speaker is Giuseppe Etiope. And I'm Jen Blank. I'm sitting in for Adrian Brown and other members of the SETI staff. I'm a former SETI research scientist and left in 2011, and I work over at NASA Ames. So it's my pleasure today to welcome Giuseppe Etiope to be the speaker for the seminar. And I welcome anyone who wants to move up now, please do, because we have lots of room in the front. Don't be shy. There might be time for questions at the end. Anyway, Giuseppe is here visiting at NASA Ames Research Center for about 2 months, and he is a senior research scientist and geologist at the Istituto Nazionale di Geofisica e Volcanologica in Rome, Italy. And essentially, that's the National Institute of Geophysics and Volcanology. Did I do okay? Where he has worked for more than 20 years studying the origin and distribution and occurrence of abiotic methane. So essentially, he's a methane guru. And this doesn't have to do with things from cows. It has to do with abiotic methane that's in the ground and how I guess the possible consequences for the environmental damage or energy resources. And also in the past 10 years, he's published several estimates of the global methane flux, which is, as we well know, that methane is now considered to be a primary greenhouse gas on Earth. More recently, he's been working with Dorothy Oler and others and Dorothy's a colleague of ours at Johnson Space Center, to identify, using Mars imagery, some of the places on Mars where we think might have the highest likelihood of methane seepage. These include things like polygonal faults, mud volcanoes or remnants of mud volcanoes, and also places where there are ultramafic rocks or rocks high in magnesium and iron that might have been previous or prior serpentinizing systems. Giuseppe has published over 165 articles in peer-reviewed journals, so he's quite prolific. And last year, Springer just published a book of his on the methane gas seepage. I've known Giuseppe for about 5 years, and I know a few other things about him, like he eats raw pasta without complaint. He likes red velvet cupcakes, has diverse musical tastes, and also even in the field, he dresses with fashion. So it's my pleasure to introduce or to hand the microphone now to Giuseppe, where he's going to talk about methane.
Thank you, Jennifer. Thanks for inviting me today, and thank you everyone for coming. My research activity in the last 20 years focused on the geologic origin and migration of natural gas on Earth. So I'm basically a petroleum geologist and geochemist. And when I approached the question of methane on Mars about 7 years ago, thanks to collaborations with the European Space Agency first and NASA then, I became aware of a gap in communications and even a lack of collaboration between atmospheric physicists and chemists engaged in understanding the origin of methane detected in Martian atmosphere, and geologists. And considering that geological processes are probably a main source of methane in the atmosphere. So you know that there is an important concept that is the terrestrial analog. It's an important concept for planetary geology, planetary science. And I believe that this concept of terrestrial analogs has not been properly considered with reference to methane on Mars. So today, in this respect, I would like to provide the perspective of a geologist. And we'll see that knowing geologic methane release on Earth is a necessary step towards understanding what's happening on Mars. And so we will use a geologic and geochemical concept of methane release on Earth. We will see this concept of seepage that is very important and has never been applied to Mars. We will use this concept to discuss potential methane release on Mars. So we'll see briefly why methane on Mars is so important. We will see the basic concept of geologic methane origin on Earth and then the potential geologic origin on Mars. Then we go to the gas seepage, gas release on Earth, and we'll see what could be the potential seepage on Mars. So a simple linear scheme of concepts. So why methane on Mars is so important? Methane has been detected in the last 17 years with the different techniques based on telescopes, orbiters, and even through ground-based observations, more recently by Curiosity rover. And the concentration ranges from less than 1 ppb, 1 part per billion, to roughly 60 ppb. So relatively low concentrations compared to other gases in the Martian atmosphere. Still, these amounts are important. Important because we know that methane can be produced by microbes, so there is a link with life. So methane exists on many planets of our solar system, of course. But Mars is the planet where there is the higher possibility for methane to be biotic. This is because Mars is similar to Earth in many ways. The geologic formation process and climate history, there was a lot of water in the past on Mars. So of all the extraterrestrial planets in our solar system, of course, Mars has the greatest potential for life. The link with microbial life is this is the main link. We know that we consider methane as a possible product of life because it can be produced by microbes or by degradation of ancient organic material in the rocks. So methane as a product of life. And when this happens, when we see that methane has a biotic origin, right? But methane can also be abiotic. And also in this case, we have a link with life, because in this case, methane can be a precursor of life. Methane can be an electron donor, can be energy source of life, as we are going to see in more detail about this concept. So for any origin of methane on Mars, we may find a link with life. An important concept to remember is that while not finding methane would not rule out life, finding methane would not necessarily imply that life exists on Mars, okay? This is an important concept. So let's go now directly to the point of a geologic methane origin on Earth. We have to understand the following. We distinguish two main classes of methane. The modern methane that is produced today by living microbes in the recent organic material in shallow sediments, in wetlands, in lakes. So there's a microbial methane today produced on Earth. But the largest amount of methane on Earth actually is a fossil. Fossil means that is radiocarbon free, and this is a geologic methane. So it's methane produced in the past by biotic processes. So this includes the microbial or thermogenic gas generally associated with petroleum, and this is the natural gas driving global economy. So what is the difference between these two microbial? This is happening today. This is modern. This happened in the past with past microbes. And this is in shallow sediments, in water bodies today. This is in the rocks. And of course, the other biotic one is when the temperature degrades the ancient organic material in the sediments in the rocks, and so we may have hydrocarbons. We have also abiotic methane that has nothing to do with microbes, nothing to do with the organic material in rocks. It is just produced by chemical reaction of a wide range of temperature, from high temperature to hydrothermal magmatic systems to low temperature systems. In particular, in the peridotites, in the ophiolites, we are going to see in detail this environment and this process of a biotic methane origin, because this is what may happen on Mars, because we know that there are similar rocks exist on Mars. Another point to consider that volcanoes don't release methane. They release only trivial amounts of the methane. Volcanoes release only carbon dioxide. So at least on Earth, volcanoes are not a main source of methane. And we should remember this point when talking about geologic origin of methane on Mars. Abiotic methane on Earth, we can distinguish about at least 9 specific mechanisms of methane generation by this chemical reaction at a high temperature related to magmatic environment to gas-water-rock reactions at low temperature. The main message here is that magmatic or mantle-derived methane is abiotic, of course, but not all abiotic methane comes from mantle. Generally, many people, many scholars associate the name abiotic with mantle. That is not correct, right? Actually, we are observing that the largest amount of abiotic methane on Earth are produced in low temperature systems and specifically by Fischer Tropsch Type reactions. We are going to talk in more detail about that. So these low temperature Fischer Tropsch Type reaction on Earth are associated to a geologic process called serpentinization. That is the transformation of olivine in the peridotites to secondary minerals. So we have a reaction with water, hydration of this rock, so reaction between water and olivine. At the end of a series of reactions, we can have production of hydrogen. So serpentinization produces hydrogen. If hydrogen meet and react with carbon dioxide that can have different origins, can be from the atmosphere, from carbon-bearing rocks, limestones, from the mantle, and in presence of a metal catalyst, a mineral, we can have the Fischer Tropsch type reactions. The simplest form of a Fischer Tropsch type reaction is the Sabatier reaction. So carbon dioxide, hydrogen gives methane on the surface of a metal. The important point is that hydrogen and methane that are abiotic, here there's nothing related to organic material or microbes, right? They can be energy source for microbes. Microbiologists say they can be electron donors for prebiotic chemistry. And actually there are many papers today discussing serpentinization as a source of energy at the origin of life, like this one, written by Mike Russell. So this is a fundamental reaction, the Sabatier reaction. You see that this represents the transition from inorganic to organic chemistry. And we need a catalyst because carbon dioxide and hydrogen don't react in air. They need to be absorbed on a metal. There is a series of reaction, physical reaction on the catalyst, and then production of methane. This is a Sabatier reaction. And so, according to recent theories, this abiotic methane can be a first step in the origin of life. So it's very important process. Serpentinization, generally many geologists, even today, remember that serpentinization happens only on the ocean floor. This is a classical serpentinization, high temperature hydrothermal systems along the mid-ocean ridges. Today we are acquiring a lot of data. We observe that we can have also continental serpentinization. So when the peridotite is hydrated by meteoric water. So while in the ocean floor, the seawater hydrates the peridotite. In this case, we have meteoric water. And this is a low temperature system. Something like that. So we may have meteoric water producing serpentinization, the peridotite that is on the continent, that is abducted on the continent. And if there is a carbon dioxide somewhere, and then if there is a special kitchen, a special rock where the two gas may meet, react with catalyst, we may have methane, and that along faults can find a way to get to the surface. Okay, and this is generally what we observe, actually we observe on Earth. And so far we have discovered at least 20 sites around the world with this kind of a biotic methane related to serpentinization, to continental serpentinization. And more or less the sites have the same characteristic. The seeps are along a fault, on peridotites in contact with limestones or rocks that can provide carbon dioxide, and always with a special catalyst that we are going to see in a few seconds. Not all of them, of course, but all the European ones, and then we can see something about what happened 2 weeks ago. And then I went to in the Emirates. Yeah. How to distinguish, to understand that this methane is different from the classic methane? We use a traditional diagram that is based on the stable carbon and stable hydrogen isotope composition of methane, where we see that the classic natural gas has this genetic field in this diagram. And the abiotic one, especially the methane from serpentinization systems, is a little bit more carbon-13 enriched and has a wide range of stable hydrogen isotope composition, but it is in this diagram is distinguished from the biotic one. There is some overlap, of course, and in some cases, of course, we need additional proxies, additional geochemical parameter to distinguish, to understand that the methane is a biotic. But this is a useful first step. And these are all the published data to date of this serpentinization-related methane. So you see that is different isotopically from the thermogenic and microbial one. There are a few cases of methane from serpentinization system with some microbial of mixed gas, but these are special cases. For your curiosity, we have this kind of methane also here in California. There are at least a couple of sites where this methane has been found, and also some potential sites around here that we need to investigate more in future. Just 2 weeks ago, with Jennifer, we went to visit the Aquadene Springs near Mount Shasta, North California, and we actually discovered another place, a seep with abundant abiotic methane. This is a spring along a creek. Creek in geology means the fault, and you see that the concept, I will repeat, this is a story of the fault many times because this is really important for us. So these springs are always along faults. We see that we have measured the pH of water, and it's hyperalkaline, very high pH, above 12. And this is typical of active serpentinization. So a lot of bubbling gas, we sample the gas. We perform a first isotopic analysis, and that's the typical abiotic methane. Also, for your curiosity, just for some fun, I would like to show you some pictures about what is probably the largest abiotic methane seep on Earth. And the name is Chimaera, is in Turkey, in Antalya Gulf. The name Chimaera refers to the legendary monster told by Homer in the Iliad, killed by the Bellerophon. So a monster sent from heaven, not human born, with head of a lion and a serpent's tail and body of a goat. So this is Chimaera, and this is a Bellerophon hero. And actually today, Chimaera is this one, and probably the monster is this. You see the head? So Chimaera is an outcrop of peridotite with a lot of cracks, a lot of gas escaping from the ground, burning. This is something that is active since at least 2 millennia, because it was reported by ancient writers like Pliny the Elder in Historia Naturalis. So can you imagine the amount of abiotic methane produced over this time and released into the atmosphere? And we measure, of course, this is something, again, along a fault between peridotites, hydrogen, and limestone, carbon dioxide. And we measure the flux, of course, is not only from the visible manifestations, but is throughout the area. So we have exhalation, diffuse exhalation of methane everywhere here. An important point, very important for Mars, is the story of the low temperature. All these systems are low temperature, are geologically low temperature systems. In geology, low temperature means something below 100 degrees. So there are many papers that recognize that this continental serpentinization at low temperature, and also we have geochemical and geological data showing that this abiotic methane is produced at this low temperature. But if you talk to experts in catalysis, expert on Sabatier reaction, everybody would say, oh, but this is the traditional catalyst like iron, nickel, chromium that is generally considered by many geologists, of course. They are effective only at high temperature. They work only if temperature is above 200 degrees. So how can they cannot support this abiotic methane production at this low temperature. So what is the catalyst? Well, I went to see a paper published in the end of the 80s by experts in catalysis. So these guys were not geologists, just chemists working on catalysis. And they found that the Sabatier reaction can be supported by ruthenium oxide. And since then, the ruthenium-based Sabatier reaction is widely used in industrial catalysis for many applications, including application in the International Space Station, where carbon dioxide breathed from the astronaut is removed thanks to this system. So ruthenium is a powerful catalyst, can work at all temperature, even a low temperature. So the question was, okay, but can this ruthenium be the catalyst for abiotic methane generation on Earth? And ruthenium is this one, is present as a mineral and oxide in the chromitite. And chromitite is a kind of rock that is in the peridotite massive, in the ophiolites. And everywhere we have these seeps of abiotic methane, there is always chromitite around. So, and ruthenium. Ruthenium is a platinum group element, similar to platinum. So everywhere in this area, there are or chromium mines or platinum group elements mines. So maybe a coincidence or not, but anyway, we tested the ruthenium in a laboratory experiment using the same amount of ruthenium that are in the chromatites. And in a very rough way, in a very dirty way. And still ruthenium can produce actually methane at very low temperature, even if the concentration are very, very small. So main hypothesis is that chromatites are possible source rock for abiotic methane because they have this special catalyst. Anyway, ruthenium or not, we have to remember that there's a Sabatier reaction that is the transition from inorganic to organic chemistry, and so is a way to generate energy source for microbes can occur in rocks at low temperature. So we don't need hydrothermal systems for this kind of important transition for prebiotic chemistry. And these are, of course, important implications for Mars. Okay, now let's go to see what is the potential origin of methane on Mars. This is a general scheme of three big categories of methane source on Mars. The exogenous source, where methane is transported from the exterior, from the space to the planet by meteorites or comets. Even there are recently some scholars that don't agree with this possibility. And then a biological origin with the microbes living today, or geologic, with methane from volcanoes. We'll see that volcanoes are not good source of methane. But this is a classic scheme. And geochemical processes, very generic. We can see some more detailed scheme like this one provided by NASA JPL, but still this can be improved because you see that there are some a little bit misconceptions, like the fact that the olivine react with water and produce methane. No, this is a reaction that this is the serpentinization produce hydrogen, not methane. And also there is a way of degassing only related to clathrates, special gas hydrates that can, like in permafrost. This is not the only way. And the outgassing is just generally described. So we can improve this scheme. And this is a proposal where we should distinguish the sources, the pathways, and the surface manifestation. So we have two different, we may have exactly like on Earth, we can have a biological methane, so with microbes producing methane today, but always underground. It's impossible to have microbes on the surface of methane today. And then all geological methane that can be biotic, ancient microbial, ancient thermogenic production from organic matter in the rocks, like on Earth, and then the abiotic methane from low temperature to high temperature systems. What is very important is that for all these production systems, we need faults, we need a preferential pathway of release of gas. And important so to distinguish between the production system. So terminology is important because otherwise there may be some confusion and misuse of terms. So these are the production system and must be distinguished from the seepage system, that is the preferential migration pathways and the surface manifestation, and we'll see more detail about that. So I just want to focus on this low temperature production system, the Fischer Tropsch Type reactions. So the question is, can this type of low temperature reaction occur on Mars? Yes, because we have all the ingredients. All ingredients required for this reaction are available on Mars. We have plenty of carbon dioxide from the atmosphere, from the deep rocks, from probably very deep magmatic systems. Remember that there are volcanoes, ancient volcanoes on Mars. We may have hydrogen from serpentinization because serpentinized rocks are being discovered on Mars. And we may have also metal catalysts, especially ruthenium, because ruthenium has been discovered in meteorites coming from Mars. We have today on Earth example of peridotites with chromite and with ruthenium. So we have everything we need to produce this low temperature methane on Mars. Now let's go to the other point is that once this methane is formed, how can it be released to the surface? So we talk about seepage. What is seepage? Seepage is a visible or invisible, focused or diffuse exhalation of methane. It is basically the result of a gas migration mechanism driven by advection. Advection is when we have to apply the Darcy law, so the gas moves because of pressure gradients and permeability, not diffusion. Some scholars still today talk about diffusion of gas, but at least on Earth in geology, in the porous media, in geologic media, diffusion is not important. So advection is the way for gas to move a long distance in a relatively short time. And the term gas seepage so is a synonymous of hydrocarbon degassing. It is a concept widely used in petroleum geochemistry and geology, so the term, don't confuse the term seepage with what some hydrogeologists say about groundwater seepage. No, this is a gas seepage, and so it's a leakage to outside from something, okay? And more details, anyway, are reported in this in this book recently published by Springers. So we need a pressurized reservoir, faults, and on the surface we can have focused, visible manifestations or microseepage. And this is very important for Mars because we don't see anything. This is invisible. It's just exhalation, diffuse exhalation of gas, a sort of a soil respiration. Some examples of microseeps on Earth, fault. And so with the special degassing along this fault, here you see there is no vegetation growing here and some gas burning. This is an example from Greece. And we can have also spectacular manifestation of this release of gas with the burning gas in many countries. This is along a fault is an example in Azerbaijan. So a huge amount of gas. And also this an example from Iraq. So this crater was not produced by a bomb because of the war in Iraq, but this is a natural seep, and probably is active since more than 4 millennia because it was reported by ancient writers. And so you can imagine also the amount of gas. So this is not a biotic, this is a thermogenic, it's a biotic. This is related to petroleum field. Anyway, this is just to show you some example of seepage on Earth, but obviously we don't consider this kind of seeps as a terrestrial analogs for Mars. We don't expect this happens on Mars, of course. But we may expect on Mars something like this, the mud volcanoes. Mud volcanoes are a special type of seep. The term volcano has nothing to do with volcanoes, just because we can have a production of a cone-shaped structure due to the release of a three-phase system with gas, water, and mud. Okay, so we have methane, cold water, and mud. We can have many, many examples of mud volcanoes on Earth. Everywhere there is petroleum, there may be mud volcanoes. Small structures that can be less than 1 meter big, or giant structures like in Azerbaijan where sometimes we can have a production of islands in the Caspian Sea, or you can enjoy to look at the Google Earth and see these nice structures in Azerbaijan. So these are mud volcanoes with methane released from the crater also throughout the flanks of this mountain. This is a map showing the global distribution of seeps, mud volcanoes, everything on Earth. So there are many, many thousands of seeps on Earth, basically distributed along hydrocarbon fields and faults. Microseepage. This is maybe very important. So we don't see anything. We may know roughly a geological distribution of the area that may host potentially may host microseepage, and this may happen everywhere there are the hydrocarbons and faults and sedimentary basins with the organic matter that was converted into hydrocarbons. We can have also microseepage, this invisible exhalation for abiotic methane. So all this is for the traditional thermogenic gas, right? So this is the petroleum related. Now I'm going back to the abiotic methane, and actually we found examples of microseepage of this invisible emission for this abiotic methane in many areas. This is a Chimaera we have seen before along a fault. You see this is the peridotite outcrops with all these flames, right? But along the same fault system, we discover some areas with this invisible exhalation. This can be detected only by special instrumentations. Also in Spain, another example of microseepage in the peridotite. We are around Ronda, between Ronda and Malaga in South Spain. So these are faults. Here's a main spring with a lot of methane. So this is visible, and people go there, okay, we see the bubbles. But we detected also this invisible exhalation far from the spring, independently from the spring, along faults. This seepage emission of methane on Earth is so important that also it represents an important source of methane for the atmosphere. These are estimates for this emission is about 60 million tons per year of methane from different types of seeps. The abiotic methane seepage still needs to be estimated because we are discovering this seepage of abiotic methane only recently. And remember, volcanoes don't release methane. Anyway, this geological seepage represents the second natural source of methane after wetlands and is comparable with other anthropogenic sources. And this is now endorsed by the Intergovernmental Panel of Climate Change, IPCC, in the recent reports. Well, how to detect this seepage? And this is also important in the perspective of exploration of Mars. This is we can detect this seepage looking for anomalies of methane in the air, above ground measurements with different techniques, or just watching in the soil, in the ground, so ground measurements, or in many cases, we can have also seepage in water bodies, lakes, in the seawater, in the oceans. And of course, these techniques are good if seepage is strong, if we can have relevant flux of gas, and so anomalies of methane also in the atmosphere, despite there may be wind, dispersions. In case of very low seepage, the best technique is that based on ground measurements. So we have to look at the soil, what's happening in the soil. We have to look for methane in the soil. And this is the approach that should be adopted for Mars. So this is the approach that we often follow on Earth, and thanks to these techniques, we discover a lot of petroleum fields in the world. Petroleum industry in the last century used a lot of these techniques for detecting petroleum fields because of the seepage from the reservoir. Or we can use the accumulation chambers, just to put chambers on the ground where there is a gas exhaling from the ground, so the gas concentration build up in the chamber, and so we can measure the flux. And this is a technique widely used in biology for ecosystem studies, for soil respiration. So this is what's happening on Mars and what we can on Earth and what we can do on Earth. Let's see if the same can happen on Mars. The first point is why gas seepage should exist on Mars. Well, the point is that methane that has been detected in the Martian atmosphere has a very short lifetimes, probably 300 years, but some scholars start to say it might be much shorter, probably hundreds of days. So this means that methane that we see today in the Martian atmosphere must be released now or very recently. It's not from millions or billion years ago, right? So this means that the presence of methane requires a geological, recent, or active source. We said that this is a seepage. This is seepage. So we need these structures that are surface manifestations of release of gas produced in one of these ways. Where we can find seepage on Mars? Where? We need the faults, remember? Serpentinized rocks, because they produce hydrogen, and then we can have methane because of Sabatier reaction. And then sedimentary rocks, because they may have ancient organic material. Faults on Mars. Mars has a lot of faults. Probably there is no plate tectonics on Mars. It's still today, Mars is considered a one-plate planet. But there are many faults related to local tectonic movement. So these are all the faults. Or many faults associated with the dichotomy. Dichotomy is this boundaries, this divide between the southern islands and the northern islands, probably produced by an ancient big impact of a meteorites. So we have a lot of faults on these boundaries, or faults associated with the craters anyway. These are an example of faults at the dichotomy, so the limit, at the boundary between the lowlands and the highlands, and this is a kind of these faults. And we'll see in a few seconds that this is a very special place. We can have a tectonic faults with the displacement of rocks, like on Earth. These are wonderful structures, and these should be permeable. These should be preferential pathways of methane for release. We have many examples of this. We have Olivine-rich and serpentinized rock on Mars. Bethany Hellman from Caltech did a great job on this. She mapped a lot of areas with olivine and serpentinized minerals. And one special place is this Nili fossa here. That is exactly the place where a significant plume of methane was detected some years ago by Mumma. And so this is a place where we have the serpentinized rocks, we have dichotomy faults, and Mumma detected this methane plume. Maybe a coincidence, maybe not, we don't know. Other important point, mud volcanoes. We have seen the mud volcanoes on Earth. Well, another scholar, Dorothy Oller, from Johnson Space Center in Houston, did a great job mapping thousands of these structures in Acidalia planitia. We are in the highlands. And it's probably more than 40,000 mud volcanoes, or something that is very similar to our mud volcanoes, I would say. These are like this one. These are on Mars, very similar to what is on Earth. We can see these weird lobes, like mud flow structures. These were fluid in the past, or like this one, flow-like features from a mound and from a central crater. So this is another recent work in Arabia Terra by some Italian scholars, and they observed these mounds aligned along a faults that is typical of mud volcanoes on Earth. So this seepage along faults, the morphology is exactly the same. So this is a very intriguing and interesting process to study on Mars, because these mud volcanoes can be really preferential pathway for methane release on the atmosphere. A few last questions. Can gas seepage flux, at least as we know it on Earth, can they support the atmospheric methane concentration on Mars? Yes, because if we bring the same seepage, a few seepage or a few seeps that we know on Earth, we bring them on Mars, they are more than enough to support the concentration of methane in the Martian atmosphere. So one large mud volcano or a few small seeps or very weak microseepage distributed in different zones of Mars will be sufficient, will be enough to provide the amount of methane required to maintain the 10 ppb background atmospheric level of Mars. So it's not a problem. Another interesting question could be, can gas seepage be detected by Curiosity rover today? That Curiosity is in the Gale crater, is working the Gale crater now. The answer is no if seepage is low, especially if there is only microseepage. Because measuring methane in the atmosphere above the ground may not work. We may not detect any signal of seepage. We need, as I showed you before, we need to go into the soil to put our instrumentation, our probes into the soil, or use the accumulation chambers. And focusing on seepage is important also for other reasons, of course, because we can find higher concentration of gas, so less ambiguous data. We have a more clear link with the geological setting. If we measure methane in the atmosphere, we don't know if methane is coming exactly from the same place where I am, or it is transported horizontally by winds. If I measure methane in the ground, that is the place where methane is coming from. And then also important is that detecting, measuring methane in the ground imply a lower molecular isotopic fractionation, some lower alteration that gas may have during migration. In the atmosphere of Mars, many chemical reaction can happen, and so the molecular isotopic composition of the gas may be different from the original one. However, the Gale crater is not the best site to look for methane seepage. There may be better sites. Well, we should not invent anything special because the technology for seepage detection on Mars is already available. We can just consider and adapt some robotics we are using for Mars. For example, for the next InSight mission, a drill hole is going to be performed, a small borehole, a small drilling, but this will be used only for measuring the temperature. So only 2 thermometers will be placed in this borehole. And also a seismometer will be positioned on the ground of Mars using an arm with a dome like this one. And this is very similar to what we do on Earth. So we can use more or less the same system as a sampling tool that can be connected to methane gas sensors. Okay, this is the summary of what we have seen today. We have to distinguish the geologic production system that can be abiotic, biotic. We need the faults in sedimentary or serpentinized rocks, but we have to use a proper sampling techniques to detect this seepage on Mars because above ground measurement may not be effective, right? And this microseepage may be, probably in my opinion, is what may happen more likely on Mars. So take home message. Probably there is the risk that analyzing methane isotopes and other trace gases, other hydrocarbons associated with methane in the atmosphere will not be decisive to understand methane origin because of alteration of the gas. Probably we'll get more questions than answers. So gas should be analyzed in the Martian soil. We should look at this gas above or near faults, at Mars volcanoes, in the regions with the serpentinized rocks, in the region with fractured sedimentary rocks. Ideally, by drilling into the soil or using accumulation chambers. And these are the same techniques that we have used on Earth to discover hydrocarbons in deep rocks of our planet. Well, thanks for your attention. Thank you very much.
That was an awesome talk. Thank you. We have time for questions.
A couple questions. The first has to do with a chart that showed the lifetime of methane in the atmosphere. There were 2 numbers. There was 300 years and there was 200 days.
Yeah, this is a controversial point.
Oh, okay.
Because, officially the consensus is 300 years, more or less 300 years. But more recently, some French scholars, Forget and others, I don't remember the names, they suggested that near the ground there may be a more stronger oxidation process that destroy methane in a very fast way. And so near the ground, the lifetime may be much shorter, around the orders of 200 days, probably some a few days. But of course, this is a big debate, and this is an important point, actually.
And my other question was having to do with the abiotic origin mechanism involves limestone. Limestone is, I thought, of biotic origin.
We need limestone only because we need carbon dioxide. And on Mars, we don't need limestone because there is plenty of carbon dioxide in the atmosphere.
Hello. You didn't mention much about the huge accumulation of methane on Earth as methane hydrates. Could a similar mechanism have existed on Mars when Mars had water?
The hydrates
is that considered biotic or abiotic?
No, this is an important point. hydrates or clathrates are not a kind of production of methane. They don't produce methane.
How did they start?
They are just a temporary reservoir where methane is stored. And this is because the ground may be frozen, so because of the low temperature, because of the pressure temperature condition may form these ice-like structures, so the hydrates. So clathrates are not source of gas, of methane. There is no production of methane in the hydrates. These are just one component of the seepage system. They may be just a temporary storage, temporary reservoirs of methane. And these clathrates may have a biotic or abiotic methane, depending on where they are.
But could it have occurred on Mars too?
Yeah, this, I'm talking about Mars. Yes, exactly.
Giuseppe, where people have put in sort of in situ gas flux monitors on Earth, like Chimaera, do they see episodic pulses of methane, or is it really a constant seepage?
Depends on where. Of course, seepage can be episodic, and we measure the big variation of flux over time at the scale of hours, days, even years, because the flux is the result of a pressure gradient. And so every time there is a pressure build-up in a rock, then we may have a rich charge and the discharge of gas, of fluids. So this results in pulsation of seepage. So actually, yes, we can see a variation of flux depending on the atmospheric conditions, depending on the wind. So if we have a strong wind, we may have the Bernoulli effect that recall more gas from the ground, so depressurization, and so enhanced migration.
So spikes of methane.
Spikes is,
followed
yes,
by
that's
much
normal.
lower
Yes,
normals.
that's normal.
And if we were to look for methane on Mars below the surface, I mean, how deep would you recommend going?
Oh,
I know it's a difficult question, but I mean, just in other words, you showed insight.
the scientists would say go deeper as you can.
Insight's going to go to, I think the probe is going to go up to 2 meters.
Yeah.
So is that deep? Is that deep enough?
At least a meter, 1 meter.
Is that deep
at
enough?
least. Then deeper is better.
Yeah.
And this is just a matter of technological capability.
On Earth, I mean, when you showed
We're gonna sometimes alpha meter is enough. 50.
I know it depends on the regolith and the
Yes,
soil.
sure.
and
Depends
this
on
and
the soil. Yes, alpha meter, 1 meter is enough. Okay.
that. Oh, great.
At Woody Point in Newfoundland, there is a place called the Tablelands, where you can see Earth on one side and Mars on the other. It's a peridotite, and there's very little vegetation on the Mars side, just in little gullies. Is there any sort of analog to Mars there?
In the Tablelands?
Yeah.
Yeah, that is one of the several places in the world with these. Yeah, we have seen like a little bit. One moment. You're referring to. Yeah, to this place, right? Yeah, this is one of the sites with as an ophiolite, Tableland ophiolite, with the chromatite, and with a hyperalkaline spring with a biotic methane. Yeah, so the analogy with Mars is that we have the same type of rock that can be on Mars. Yes, and this is also another low temperature system, and still we have a biotic methane.
So in your low temperature catalysis experiments, these were done with pure ruthenium, or did you also use chromatite with a known concentration of
I
ruthenium?
had to use pure ruthenium oxide, but in the same form as it happens in the rocks. I tried to use the chromatite, but I found that the chromatite already have some methane inside.
Huh.
This is another point.
So how do you, if
that-
you trap methane there, how will the methane come off?
Yeah, so I may have
How
a
we get it?
contamination.
Yeah.
Otherwise, I don't know if the methane that I'm observing was generated by my subatomic reaction or was already there because it was already in the rock. And actually, we are observing that in many places, these rocks have a lot of methane inside.
So I guess there's some
So even independently of these seeps, everywhere we have these chromatites with platinum group elements, we may have a lot of methane in the structure. So this is the subject of a recent research that is very important, I think.
Cool. Are there other questions from the audience? Oh, another one. Good.
Some decades ago, I read that I think it was Tommy Gold had a hypothesis of deeply buried methane. Do you know how deep he was talking about?
He was referring to mantle or deep crust. At that time, there was no clear idea about Fischer Tropsch Type reactions. And no, he was mainly referring to something very, a deep production, mostly related to mantle. So that was the source of confusion between when we say abiotic, and then we associate by abiotic means mantle, means deep, very deep source. No, it's not necessarily deep, because all these geological settings here refer to peridotites that abducted above the continent, and this is relatively shallow. So this methane is likely produced at not deeper than 2, 3, 4 kilometers. So it's not really deep to the root of the earth or deep in the mantle, absolutely not.
Did you have a question? Oh, okay. So it's nice you have this map up here. If you had to pick one or two places you want to go to next to look for methane, where would it be, or where would they be?
I bet, so there are many of these sites are associated with hyperalkaline springs. I didn't mention that every time we see, we have a spring with pH above 10, above 9, so when it is pH is 10, 11, 12, hyperalkaline. This is a direct indication of a serpentinization. So there are very good chance to see abiotic methane. So there are still a couple of sites on Earth where we have these hyperalkaline springs, but nobody has ever tried to verify if there is methane. One of that is Cyprus. So I bet there is abiotic methane on Cyprus, and then in Serbia and in Bosnia as well. And probably there are other places around the world.
Cool. So in keeping with the SETI tradition, we have a small token for you. And on behalf of SETI and Adrian Brown, I'd like to present you with this mug.
Oh, thank you very
And
much.
thank you very much for your talk.
Thank you.
Let's thank him.
Thank you.